All right, we're going to do a quick review of atmosphere, and we're also going to talk a little bit about Coriolis effect in this video, hoping to keep it under our 15-minute time limit. So if you take a look, the structure and composition of the Earth's atmosphere is made up of a variety of gases, and each has its own relative abundance. And the layers of the atmosphere are based on the temperature gradients, and there are several layers. So we're going to talk about those briefly here in the introduction. So in the atmosphere, you've got nitrogen, oxygen, argon, water vapor, and CO2. So nitrogen is the majority of our Earth's atmosphere with 78%, mostly in nitrous gas form, which is unusable to plants and animals without being fixed. So we have a whole process called the nitrogen cycle that we'll learn about a little bit later on how that gets into a usable form. 21% is oxygen, which is produced by photosynthesis in plants, also algae, so the ocean, very important for us as well. Argon is an inert noble gas, very little of that in the atmosphere. Water vapor varies by region, but it's anywhere from 0% to 4%. It can act as a temporary greenhouse gas, but it quickly cycles through the atmosphere and the Earth. CO2 is 0.04%, which sounds very small, but it's the most important greenhouse gas that leads to global warming. It is removed from the atmosphere through photosynthesis. The other greenhouse gases we'll talk a little bit more about later, but these are all the naturally occurring greenhouse gases that we see on Earth. So the layers of the atmosphere, there's the exosphere, that's the outermost layer you can see in this picture. I'm sorry for moving my face around here. The exosphere, that's where we have, the outer layer of the atmosphere that merges with space. The thermosphere is the hottest. It absorbs the harmful UV rays. It is where we see northern lights, and the gas molecules, the charged gas molecules will glow under intense solar radiation, which is what gives us sort of that view of stars, the furthest stars out. The mesosphere is for the middle. That's the least dense. It's about 60 to 80 kilometers. And then the stratosphere, think stratosphere for a second, that is the thickest layer of ozone that absorbs the majority of the UV rays that we're exposed to, which protects us from mutation of our DNA. So the stratosphere is sort of the most important of those outer layers because that's where the ozone layer exists. The troposphere, that is the layer of the atmosphere that we actually come into contact with. The troposphere, that's where we see weather, that's where we see the atmosphere's gas molecules that we just talked about. The ozone in the troposphere is not good. So when we have ozone in the stratosphere, that's a good thing. Ozone in the troposphere is not good. It's the most dense of all the layers due to the pressure of all the layers above it. But the troposphere is, think of, that's the air that you're going to breathe. If you look at the temperature gradient, the layers of the Earth's atmosphere are based on where the temperature gradients change with distance from Earth. So the thermosphere, the temperature increases due to the absorption of those rays from the sun. The mesosphere, the temperature decreases because the density also decreases, and it's actually the coldest place on Earth. So because the density decreases, there's less molecules to absorb energy from the sun, so it's actually very, very cold. The stratosphere increases because the top layer of the stratosphere is warmed by UV rays, like the top of a pool. The ozone layer is absorbing all of those, and then the troposphere decreases as the air gets further from the warmth of the Earth's surface. Sorry, I clicked too quick. So take a quick second and identify a layer of the Earth from the diagram that has an inverse relationship between temperature and altitude, and describe why this occurs. Don't spend tons of time on this one. You're probably not going to be asked a question like this, but good practice to describe the relationship between the two. So next we're going to talk about global wind patterns. The global wind patterns occur for several different reasons. So they happen from solar radiation, and the difference in density, and that causes what we call the Coriolis effect. So the atmospheric circulation that we see comes from energy from the sunlight, the density properties of air, and the rotation of Earth. And that's the activity that we're doing in class right now. So if you take a look here, these are what we call Hadley cells. And what happens is that at the equator, you have direct sunlight happening, which we're going to look at that as well. That direct sunlight warms the air. As the air warms, it rises and expands. So just like in your house, think the basement is the coldest and the attic is the hottest. So as the air warms, it rises and expands. That H2O, that water vapor that's been in the atmosphere, is going to condense into rain. As it continues to rise, it's going to cool and expand and spread out. As it cools, then it ends up sinking back down to the earth. That happens at 30 degrees north and south. And that's where we see most of our deserts because the air moisture is gone because all of that rain falls closer to those tropics. So think of that as a big circle that happens, kind of like a convection cell. Right? So at this area here at 30 degrees, you're going to have high pressure pushing back down. So because that's the air is sinking, and at 0 degrees, you have lower pressure. And so that lower pressure is going to allow the cool air to rise. So the Coriolis effect is the effect of the Earth's spin on objects in the atmosphere. So it's the deflection of objects traveling through the atmosphere due to the spin of the Earth. Air at 30 degrees moves back to that lower pressure that we just talked about at the equator. The wind from 0 to 30 degrees is going to move from east to west because the Earth is spinning west to east. And you should have seen that in your activity today. The wind between 30 degrees and 60 degrees is going to be moving west to east. That's because of the rate of spin that's happening. That's where we get what we call the trade winds, here and here. All right, these are the trade winds that are happening here. So that deflection is happening because of the speed that the Earth is spinning and the direction that it spins. So here you're seeing, we just talked about the Hadley cells. We have Hadley cells that are happening here, right? Because of that, it creates these trade winds. So like we just talked about, from 0 degrees to 30 degrees, we have those northeast trade winds. And from 30 to 60, you're going to have the westerlies. And then at the very top of the Earth, you're having the same thing sort of happening called polar cells. And here you're going to have something called ferrule cells happening. So all of these winds are due to that convection current that's happening in the atmosphere at each of those places. Okay, so again, low pressure here is allowing that to rise, and then it's getting pushed back down at those higher pressure areas at 30 degrees north and south. And then again, at 60 degrees, you have lower pressure, so that's going to cause that same sort of cell happening here. So Hadley cells, ferrule cells, and then polar cells at the north. So if you look in this diagram here, you see Hadley, Hadley, ferrule, and polar cells. So explain how the sun, so go all the way back to how the sun warms the Earth at the equator. Explain how the sun is responsible for the pattern of air circulation seen in cycle C. So you're taking a look right here. Feel free to rewind and rewatch all of those things. There's several videos on wind currents and Coriolis effect that I'm going to link at the end of this video as well for you to take a look at. I hope you guys have a great night, and I will see you tomorrow.